6.5 is called L'Hôpital's rule and indeterminate forms. L'Hôpital, or in French, I know we got French in here, right? The little nurse's hat on the O, is that a French mark? And it's supposed to make the O sound kind of like an S at the end, is that right? Or how would you say that in French? Because he was French. L'Hôpital? So that's how I've been saying it through the years. L'Hôpital. It's kind of interesting because that little mark looks kind of like a nurse's hat. And most people, when they write L'Hôpital, they do not write the nurse's hat, and they put an S after it. La hospital. A circonflexe? A circonflexe. A circonflexe. Okay, I'm just going to write it phonetically. It's called a circumflex. Okay, also a nurse's hat. Now you're telling me that it doesn't make the OS sound. No? Like in German, if you wrote this with the umlaut, it's bitterschuh, right? If you write it without the umlaut, they always add the E at the end instead of the umlaut to give the sound. But you're telling me that if we remove the circumflex, it does not make the le hospital sound? Okay, so I don't know why people call it the hospital rule. But you know what? It doesn't matter anyway, because the rule that we're about to learn was actually discovered by Johann, and I don't even know if I'm spelling this right. Johann Bernoulli? Yeah. Johann Bernoulli was L'Hôpital's calculus teacher, and Johann Bernoulli discovered the rule, taught L'Hôpital the rule. L'Hôpital then went on to, this is kind of a nice thing for like if you're ever on Jeopardy, L'Hôpital published the first ever calculus textbook. L'Hôpital published the first ever calculus textbook. And in that textbook, he included Johann Bernoulli's rule that he learned from him. But, of course, as it is in the science community, National Science Day, by the way, it's not the first to discover that gets credit, but the first to publish that gets credit. So it's called L'Hôpital's rule, and I just erased. Hang on, let me erase, because I want to keep that there. The circumflex. Okay, I never knew what that was, so thank you. All right, so anyway, this is called L'Hôpital's rule and indeterminate forms, which means y'all are going to be looking at a form and you're going to be like totally confused, okay? What is that? Is that a tree? Or is that a car? I have no idea. It's an indeterminate form. All right, so what does it mean to be an indeterminate form in calculus? Okay, so remember back in the day, early in the day, when we were pouring the foundation for the house calculus, we started evaluating limits. And we had a whole bunch of methods like rat-con, lick-em-over-lick-em, sledgehammer, that allowed us to evaluate limits when direct substitution gave us what? 0 over 0. Yeah, so 0 over 0 we called an indeterminate form, because 0 over 0 means the function is not defined there, but the limit might exist. And the limit might be 5, or it might be 10, or it might be peaches, or it might be infinity. We don't know. The other indeterminate form we encountered already was infinity over infinity. And that is like when you're taking the limit of like a cosecant to a cotangent. No, I guess it would be a cosecant to a tangent as you approach 0, or an end behavior limit. Like if you have the limit as x goes to infinity of a cubic over a cubit, that's infinity over infinity. And we learned ways to get around that as well. So whenever you're evaluating a limit and direct substitution gives you one of these two forms, we call that an indeterminate form. Now what we're going to learn now is, and look, I always use peaches. Peaches could be an answer. You just never know. We had algebraic ways to circumvent the indeterminate form to get the answer. What L'Hôpital's rule does is it gives you a real quick, direct way to circumvent the indeterminate nature of it. So let's look at this one here. Let's say we were going to evaluate that limit. Going back to the early part of the year, never not first, how do we evaluate a limit? Plug it in, direct substitution. If you plug it in, you get e to the 0, which is 1. 1 minus 1 is 0 over 0. So get in the habit of writing your indeterminate form kind of above the equal sign. that kind of shows that you've A, plugged in first, never not first, and gotten an indeterminate form. Now, are any of the methods that we learned earlier in the year going to help us get rid of this 0 over 0 problem? Factor and cancel? No. Factor and divide out? No. Sledgehammer. Well, you can hit it with a hammer, but it's not going to help. Ratcon? No radical. Lick 'em over lick 'em? No complex fraction. Trig you with it? No, no trig. So we're kind of stuck, right? So I guess it can't be done. Well, not true. If you have your calculator, remember, you can always evaluate a limit numerically by typing this function into y1, looking at its graph, and remember sneaking up to 0 from both sides to see what the y value is, right? That's always an option. So we're going to do that. We're going to sneak up to 0 from the right-hand side of 0 by evaluating the function at point 1. So the way I'll do that, since I'm going to do it repeatedly, is in y1, we'll type in our function. So get the horizontal division bar, e to the x, that's second ln to the 3x power minus 1 off to the side, and then we're going to divide by x. So remember, we don't have to do this graphically. We have it in y1, go to the home screen. If we recall it, alpha trace number 1, if we open parentheses, type in the x value of 0.1 and hit enter, we get the numeric value. So we don't need the graph, because that involves like setting a window and all that garbage. All right, so I'm going to write it down. It's 3.498. Now, is that enough information to determine what the limit is as we approach 0 from both sides? No. 0.1, in the grand scheme of things, is still pretty infinitely far away from 0, isn't it? Relatively speaking. Yeah. So let's just get a little bit closer, right? 0.01. So I'll just hit second enter, and I'll scroll back here, and I'll just put 0.1 close parentheses. So now we're 100th of a unit away instead of a 10th of a unit. Ooh. I get 3.045. What happened to my y values? Increase or decrease? Decreasing, okay? So I guess they're going to decrease forever and ever, approaching what, negative infinity? Oh, you think it's going to approach 3. So you're saying you think there's a limit to how small they'll get. We shall see. Let us inch a little bit closer at the risk of being uncomfortably close. Ooh, 1,000th of a unit away. You can not only smell someone's breath, but taste it when they're that close. Gross. All right, so 0.001. Ah, look at that. It's 3.004. So again, the y values are decreasing. Are they going to 0? Or are they going to negative infinity? Or as Gorel said, there you go, you're on the video now. Are they approaching 3? I don't know. That's all I had to evaluate. Should we do one more on our own? Yeah, we should. And you know what? We should get serious with it. We don't have to tiptoe up to it, do we? We could just get right up there in its grill, remember? So recall it. Let's go ahead and put 0.000. 1. And then, I guess the answer is 0. No, you got too close. This person like punched you in the face and now you're out. Okay? You've broken the calculator. You've gotten way too close to the calculator. It's like, Uncle, I give up. So you can break your calculator. We just did that. So let me recall that, and let me come back in here, and let's just trim it back a little bit. I don't know how many, but let's try that. Is that good? So there is a difference between like inching up to it and seeing what the values are approaching, to overloading it, getting too close, and breaking it and give you a 0. There is kind of a nice sweet spot in there that if you get sufficiently close, where it's not giving you decimals and it's not breaking, you can basically trick your calculator into giving you the answer. It was so close to 3, your calculator just went 3, and so that is the answer. And that was also the numerical evidence that we were gathering already. So based upon that, what would you say the limit is as x goes to 0 of this function? 3. Now, I just did it from one side. I better check from the other side, right? Because remember, it has to be the same for both sides. So let me just insert a negative here. Second, delete inserts. And, 2.9999995. Is it still 3? Yeah, I think the evidence there still supports 3. Okay. So there you go. Without an algebraic method, we now determine the limit. The function value does not exist at 0. The function value does not exist at 0. There's going to be a what there graphically? A hole, right? 0, 0 means hole unless it's Senor Salta. Jumpman. So there's going to be a hole, but the limit exists and it's 3. Okay, sweet. What about this one? The limit as x goes to 1 from the right of 1 over ln minus 1 over x minus 1. Never not first. Direct sub gives us what? What's the natural log of 1? 0. What's 1 over 0? It's d and e because it's some type of infinity. Now, because we're approaching 1 from the right, natural log of 1 as we approach 1 from the right is positive infinity. So that's going to be positive infinity. Minus, if we plug a 1 in over here, what's 1 minus 1? 0. And again, we're approaching 1 from the right, so it's going to be another positive infinity. So, now I ask you, what is infinity minus infinity? You think it's 0? What if one infinity is bigger than the other? What if the first infinity is 7 units larger than the other infinity? Then infinity minus infinity might be 7. What if the second infinity is 7 units larger? Now infinity minus infinity would be negative 7. What if the first infinity was infinitely larger? Now infinity minus infinity is infinity. I'm not comfortable calling it 0. Are there different sizes of infinity? Not just yes, but heck yeah. Yeah. Okay? We know that from our experience with like x cubed over x squared. X cubed and x squared both go to infinity, but which one goes to infinity faster? X cubed. There's also, and this is kind of getting off topic, there's also like countable infinity, where you can kind of enumerate a list. Never finish the list, but make sure you're not skipping anything as you go down the list. That's a countable infinity. That would be like the integers or the whole numbers. Versus a non-countable infinity, where there is no way to generate a list. That'd be like the real numbers. So non-countable infinite sets are bigger than countable infinite sets. So just know that there's different sizes of infinity. Therefore, infinity minus infinity is going to be indeterminate. Okay? That's another indeterminate form. So now we have 3. 0 over 0, infinity over infinity, and infinity minus infinity. It's indeterminate. What if it were infinity plus infinity? Is that indeterminate? That would be infinity now, because they're both going in the same direction, right? What if they were both negative? Now it's negative infinity. So the only reason that it's indeterminate is because there's kind of a tug of war. Just like infinity divided by infinity. Do they divide out, or is the top bigger, or is the bottom bigger? There's a tug of war here. They're canceling, but which one's bigger? If they're both the same sign, there's no tug of war. They're just contributing to the same direction. It's not indeterminate. All right, so do we have an algebraic method at our disposal already to evaluate this guy? Lick 'em over lick 'em. That works when you have complex fractions. We don't have complex fractions here. We have 2 terms. So none of the methods, if you kind of scan mentally through them, none of the methods that we've learned in the beginning of the year are going to help us do this. So let's go ahead and do it graphically. So again, what I'll do is I'll come over here, flush to get rid of that, and just type in 1 divided by ln of x. And again, I'm using the horizontal division bar, which works for this one, minus, if I do that for the next one, I got to make sure I put parentheses around the 2 terms. If you ever have more than one term or one factor in the denominator, you need parentheses, or use the horizontal division bar. All right, so let's just kind of quit playing around. I'm approaching it from the right. I want you to evaluate 1.1, 1.01, and 1.001. Do we need to do that? The limit, remember, is a notion of motion. So it's an idea of moving closer. And if we were to evaluate that, we would get values that would help us see the trend. But We don't have time for that, right? The AP exam is May 15th. So let's just get serious about it. Alpha trace, number 1, and let's approach 1 from the right-hand side. 1 point, well, the one I asked you is the closest is 0.001. Let's just go 0.00001. I don't know. Let's see if that works. 0.4999999. That's a very small sample. You don't really see the trend, but you're close enough that you might be able to infer what the limit is. What would you say? 1/2, right. Now, I better do just one more. I would say let's at least do 2. So let's just come back here. Let me add one more 0. If I just add one more 0, I'm either going to get more 9s, or I'm going to get to that sweet spot where I break the calculator and it gives me the answer, not break it and it punches me in the face. There's enough numerical evidence, right? 0.99999999999, and therefore, we guess that the limit is 0.5, also known as 1/2. Okay, sweet. So if you're evaluating limits and you don't have an algebraic method and you have a calculator, it's easy. Figure it out numerically. We don't have to look at the left side here because we're approaching it from the singular right side. Okay, what about this guy? We're approaching infinity now. Never, not first. Let's plug in infinity. If you plug in infinity into the inside, you get 1 plus 2 over infinity. What happens to 2 over x as x goes to infinity? It goes to 0. So the inside approaches 1 plus 0, or 1. And then you plug in infinity for x, and you get 1 to the infinite power. 1 to the infinite power is 1? 1 times 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 1 is 1? Is that what you're telling me? Okay. I agree with you. If I just gave you the number 1, and I said raise it to the infinite power, it would be 1 times da-da-da-da-da, times 1 times da-da-da-da, infinitely many times. I would agree it's 1. I would agree with that. No problem. But remember, we're talking about a limit. Do we actually ever reach 1 on the inside here? No, it's a limit itself. We are approaching 1, right, from the top side of 1, right? 1 plus a smaller fragment, so 1 plus 1, 1 plus 01. So we never really ever get to 1. So 1 to the infinite power is not really 1 times 1 times 1 forever. It's increasingly smaller values that are approaching 1 raised to larger and larger powers. Is there a tug of war there? Yes. On the one hand, you're getting closer and closer and closer to 1. You're getting smaller and smaller and smaller towards the identity element of multiplication. But on the other hand, you're raising it to a larger and larger power. And if you raise anything that's bigger than 1 to a larger power, you're going to get a larger number, right? So there's a tug of war. On the inside, we're getting smaller, and on the outside, we're making it bigger. That's a tug of war. Guess what 1 to the infinite power is? It is another indeterminate form. 1 to the infinite power, if it's approaching 1 and not just 1. Again, if it's just truly the number 1, then it's 1. But we're approaching 1. So this is an indeterminate form. It could be 7. It could be 1,000,000. It could be peaches. It could be infinity. We don't know. All right. So do we have an algebraic method from earlier in the year to evaluate this one? No, we don't. All right, so we do have the calculator. Now, the right-sided limit is a one-sided limit. So I'm not going to go to y equals because we're going to do it just in one calculation. So parentheses 1 plus. I'll use the horizontal division bar here. Why the heck not? Sometimes I get lazy. Now I can't plug in infinity per se. Well, what can I plug in? A very big number like 999 and 999, right? Something like that. Pretty big. And then I'll raise that to the, God, how many 9s did I have? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And I hit enter. Wow. And it gives me 7.389. So I'm going to write that down. I'm not going to even follow my own work down here. Because look at that. I started at 100. And then 1,000, and then 1,000,000. We're already way past that. So let's go ahead and do one last thing here. Let's go ahead and recall that. And just come back in there and add one more 9 to both of them. These should be the same size of infinity, by the way, because you're plugging the same thing in for both x's. So these have to be the same number that you plug in. So I added one more 9 to both, and I got 7.389055. So it's the same to the first 5 decimal places. So if we had to report the limit to 3 decimal places, would you be comfortable in saying the limit is 7.389? Yeah, I think that would be a safe bet. Okay, so 7.389 looks, and then of course maybe something else. It looks like maybe it could be an irrational number. That's nowhere near 1. So that proves my point. 1 to the infinite power in this case was not peaches, it was 7.389. Indeterminate. There's no way to determine that prior. All right, so what we're going to learn in this section then is we're going to revisit these 3 guys in a little bit, and I'm going to show you the way that we can actually evaluate it analytically, if you will, by using a combination of algebra and calculus. We're going to be able to find it without the calculator. And that method is going to be called L'Hôpital's rule with the circumflex in there. All right. I don't like to take that circumflex nurse's hat off. I leave it in there. Okay, so let's review, first of all, some earlier algebraic techniques for dealing with the indeterminate forms, right? Let's revisit 1.4. The limit of x goes to -1. Never not first, what do you get when you plug in? You get 0 over 0. Whenever you get a polynomial over a polynomial, then you're going to factor and divide out. Now, because -1 gave you a 0 over 0, you know the bad guy factor in the top and bottom is x minus that number, so it's x plus 1 over x plus 1. In fact, the bottom is x plus 1. So in the top, if I factor out the 2 first, I'm left with x squared minus 1, which then factors into a difference of squares. Remember, the x plus 1s divide out, factor divide out, and now the world is safe again for direct substitution, so you get -2 times 2 is -4. That's the answer. I did that fast because it's review. We did it at the beginning of the year. That was the very first method that we learned. Polynomial over polynomial, 0 over 0, factor and divide out. And that method still works, right? Here it is, later in the year, and it still works. Beautiful. All right, how about this guy? The limit as x goes to infinity. If you plug in, you get 3 infinity squared, which is infinity. In the bottom, you get 2 infinity squared, which is infinity. That's an indeterminate form. We knew how to do this one because they were growing effectively at the same rate because they were the same degree. These are effectively 0. It's approaching the ratio of 3/2. So we did have a way to get around that indeterminate form. And again, the answer is not always 3/2. It's always leading coefficient over leading coefficient. This one here, you plug in a 7 and you get 0 over 0. And what method was this? Retcon, right? You got a radical, and you got 2 terms, so you're going to multiply by the conjugate, and that will rationalize the numerator. So turn the equal sign to a multiplication, and we get x plus 2 plus 3 over x plus 2 plus 3. So remember, you change the sign betwixt the terms, not under the radical. And remember, when you plug in a 7 and get 0, that means x minus 7 is the bad guy factor. So in the bottom, we're going to leave the x minus 7 visible. So this becomes x minus 7 times the quantity, square root of x plus 2 plus 3. And in the top, that's where we multiply it out, because those are conjugates. Radical times radical is radicand. The inner and outer terms will cancel. Minus 3 radical plus 3 radical is 0. And we're left with minus 9. And now in the top, what is x plus 2 minus 9? X minus 7. So I told you back in the day we could do a shortcut. As long as we group those 3 terms together, we can call it x minus 7, and then guess what? Divides out, leaving a 1. Once the bad guy factors are gone, we can plug in direct substitution again, and we get the square root of 9, which is 3, plus 3 is 6. The answer is a 6. Ratcon. Still works. Ratcon still works. Yes. Okay. I think that's enough of a review. There were other methods. All right, so here we go. Not all indeterminate forms can be reconciled via algebraic techniques like we learned back in 1.4. Another method discovered by the Swiss mathematician Johann Bernoulli. So that is how you spell Bernoulli. It's an E in the beginning, not another O-U. Okay, so Bernoulli. Johann was the older brother of the famous Bernoulli brothers, the younger being Jacob Bernoulli. And the Bernoulli, if you look at the family of Bernoullis, the sons and then the grandsons, they're quite a family. They made many, many, many contributions to both math and science. But Johann discovered it, and he taught it to the French student whose name was actually, you want to help us with that? Guillaume. Yeah, Guillaume. Yeah, it's French. So Guillaume del L'Hôpital. Guillaume del L'Hôpital, the French guy, right? He taught it to his student, and as I told you, Guillaume published the first calculus textbook and got credit. So this is a sketch of Johann Bernoulli, and you can tell he looks pissed. He looks mad, right? And then here is an actual photograph of the dapper Guillaume le Hôpital. Okay? I don't know if that's a wig or his real hair, but yeah, he was kind of fragile, petite and fragile, right? So I'm surprised Johann didn't bully him. Just give him a stare and he'll crumble. Okay, whatever. He looks kind of wimpy, but wise. He's a shrewd businessman, right? Hey, I'm going to publish the first calculus textbook and get rich. All right. And then I get credit for this guy's work. I'm going to get you. All right. You know what? This lift might not only be directed at L'Hôpital. He might be directing that ugly look at his brother Jakob. They apparently did not get along. Okay. So anyway, here is L'Hôpital's rule, or if you want to call it Bernoulli's rule, I'm fine with that. I'm always for advocating the underdog or the guy who's the little man who's been stepped on, which is why I have the poster of Leibniz over my desk. I just put Newton over there, right? Because Newton gets all the credit, and Leibniz did not get as much credit in his day. So I like to support the guy, the little man. So we can call it Bernoulli's rule or L'Hôpital's rule. So here's what it says. You're going to love this, guys. If the limit as x goes to a of one function f of x divided by another function g of x. So we have a quotient. That's important. We have a quotient of two functions, and we're approaching a, where a could be a number or it could even be infinity. Okay, we're approaching something. If direct substitution yields one of these two forms, these are the only two quotient forms of indeterminate form. We've seen infinity minus infinity, which is the difference form, and 1 to the infinite, which is exponential form. These are the only two division forms. If you get either 0 over 0 or infinity over infinity, then you can use Bernoulli-L'Hôpital's rule, which says the limit of the quotient is equal to the limit of the quotient of the derivatives. That's fantastic. Notice this is not the quotient rule. It just says if you get 0 over 0 or infinity over infinity, take the derivative of the top, take the derivative of the bottom, which back in the day we called the incorrect quotient rule, and then try taking the limit again. And just like it says in the shampoo bottle, right? Rinse, lather, repeat. If the derivatives give you another indeterminate form when you plug in, you could take the derivative again. The limit as x goes to a of the second derivative quotient, or the third derivative. And you could keep doing that until you get into an endless loop, in which case you starve and die after 27 days. Or you get an answer, which is what we're hoping for, or you break out of that endless loop before day 27 and you try a different method, okay? So let's try it out. You want to? Yeah. Okay. Now, there are some qualifications, right? It has to be a quotient, and direct substitution has to yield one of these two. If it's not a quotient or direct substitution doesn't give you one of these, L'Hôpital does not work at all, okay? So let's go back and revisit our calculator friends from example 1. The limit as x goes to 0, v to 3x minus 1 over x. What does direct substitution give us? 0 over 0. Is that one of the two acceptable indeterminate forms? Yeah. Then here's what Bernoulli discovered and L'Hôpital shared with us. There you go. We can kind of give them both credit, right? Because Newton discovered a lot, but he was reluctant to share. And if it weren't for Edmund Halley, the comment guy, Newton might have not have ever published his calculus. So I guess it takes two people. You got people that are like not people, and they stay inside, but they have all this stuff that they keep to themselves. And then you got the marketer who brings it to the public. So we can give Bernoulli and L'Hopital credit. All right, so here's what we do. We'll take the derivative of the top, which is two terms. What's the derivative of e to the 3x? E to the 3x times the chain rule, which is 3, and then the derivative of minus 1, 0, all over the derivative of x, which is what? 1. And notice I have the limit in front again. You got to have the limit in front again. Now, let's try direct substitution once again. What do you get when you plug a 0 into the top? You get e to the 0, which is 1. 1 times 3 is 3. 3 divided by 1 is 3. Holy moly smokers. Is that the same number that we got way up here with the calculator? Yeah. Wow. All right. Did we need a calculator for that one? No. Did it even take as long? No. Was it more enjoyable? Yeah. So thank you, Bernoulli, for discovering it. And this is the first time I'm actually giving L'Hopital credit. Thank you, L'Hopital, for sharing it with the world. It started with Bernoulli. But and I don't know if like Bernoulli was like, hey, L'Hopital, I'm going to go ahead and publish this in 2 days. And L'Hopital went home that night and wrote a calculus book the next day. So I don't know if that was it, or Bernoulli was like, no, I'm not going to tell anyone about that. I'm just going to keep it to myself. And he's like, you must share it with the world. Okay, like the way you kiss and the way you make your potatoes. Right? I think Bernoulli discovered French kissing and French fries, and then L'Hopital brought it to the French market. That's just a conjecture. Okay. Letter B. Letter B. We did this one up above. What do we get when we use direct substitution? We got 0 over 0. How would we evaluate this one normally? Ratcon. We don't need to ratcon it. Let's lop it. We'll just call it lopping it, right? Let's lop it, right? Like a tree trimmer. Let's lop it. Okay? So, the derivative of the top, we got to use the chain rule. Now, can you imagine it being to the 1/2 power without me physically writing it like that? Very good. So it's 1/2 times 1 plus x to the negative 1/2 power times the chain rule 1, and then minus 0 all over 1. Okay, now that is derivative of the top, derivative of the bottom. Sometimes you might want to clean this back up a little bit before you plug in. Tyler, don't make the disgusting look. I know it looks ugly, but we're about to clean it up. That's the same as 1 over 2 square root of 1 plus x. So sometimes before you try direct substitution after you lop it, you want to go ahead and clean it up, which we did. And now you plug in direct substitution and you get 1 over 2. 1 over 2. 1 over 2. Yes, what is your question? No, the method of Ratcon and Lick 'em over Lick 'em, those are like pretty basic algebraic remedies. So it's almost like it's common knowledge, even though it was new for y'all when y'all learned it. Back in the day, the people who were like doing math, that was like no big deal. So I don't know if anyone ever got credit for those methods. Now, I gave them the name Ratcon and Lick 'em over Lick 'em. But the method themselves, I don't know. Okay, that would be like the guy who discovers 1 plus 2 equals 3. Did the first guy who discovered that get his name attached to it? No. Okay. Good question, though, Tyler. I'm glad you're thinking. You're wanting to give credit to more people. If you read like the newspaper or you watch TV, you'll hear people like say quotes a lot of the time, and very, very, very infrequently will they attribute the quotes to a person, either because they don't know who said it, but they know what the saying is, which you should kind of know who said something if you're going to quote it, or they're deliberately concealing the author to try and make themselves appear more original. Yeah. Mm-hmm. Oh, great question. Does it work in reverse? I've never tried that. But I would think if you start with an indeterminate form and you integrate it, you're going to be building it up. You're typically going to be adding things, which is going to make it look a little bit bulkier and therefore harder to integrate. So you may get another indeterminate form, but it's probably the wrong direction to help you eventually evaluate it. But I'm sure that it would work, right? Because of the, the two-way way the pipe flows. But whenever you take the derivative, remember, you're tearing things down. You're making things smaller and smaller, and so that's why we go that direction. That's a great question. Okay. All right, how about this? You're approaching pi halves. Direct substitution. You know what? We're going to have to wait because class is going to end in 30 seconds. So we'll stop right there at 3B. But now you got a feel for L'Hopital and Bernoulli.